In the last lecture, we were discussing point source and point dipole. Okay. So, point source, okay, the temperature field is equal to Q by 4 pi k into x minus the source location. Okay. So, if I have a point source at some location x s, okay, of strength q, and there is some observation location x, the temperature field decreases as 1 over the distance between the source and the observation point. Okay. And the heat flux was q into x, this is a vector x minus x s by 4 pi k into x minus x s the whole cubed. Okay. So, that is the temperature and the heat flux. We were discussing next a point dipole. Okay. Point dipole. X, y, z. A source point, okay, of source strength plus q, and the sink minus q, okay, separated by a distance L. Okay. And we are looking at the temperature field at some observation point, which is x, due to the combination of the source, which is emitting heat, and the sink, which is absorbing heat. Okay. In the limit where L is much less than the distance from the origin. Okay. So, when the distance to the observation point is much larger than the distance between the source and sink, what is the temperature field due to this? Okay. What is called a point dipole. Okay. So, we have written the temperature field as q by 4 pi k into the distance to the source point, that is x square plus y square plus z minus L by 2 the whole square root of, okay, minus 1 over square root of x square plus y square plus z plus L by 2 the whole square. Okay. Okay. Because this sink was at 0 0 minus L by 2, and the source point was at 0 0 L by 2. Okay. The source is at 0 0 L by 2 and the sink is at 0 0 minus L by 2. Okay. Okay. And then I had used a binomial expansion in the limit where L is much smaller than x vector. Okay. So, therefore, okay, square root of x square plus y square plus z square, okay, plus the whole square whole to the power of minus half. Okay. This can be written as x square plus y square plus z square minus Lz plus L square by 4 whole to the minus half. And x square plus y square plus z square is just r square. Okay. So, I will just get r square minus Lz plus L square by 4. Okay, to the minus half. This was written as, I take a factor of 1 over r outside, and I will get 1 minus Lz by r plus L square by 4 r square whole to the minus half. Okay. And you can use the binomial expansion to simplify this term. Okay. So, this just becomes equal to 1 over r into 1 minus Lz by 2 r square plus 3 L square Z square by 8 r power 4 minus L square by 8 r square. Okay. So, this was what I had got for the binomial expansion of the distance. Okay. So, this one was equal to x square plus y square plus z minus L by 2 the whole square to the minus half. Okay. If I take the other term, which is x square plus y square plus z plus L by 2 the whole square to the minus half, this I just have to reverse the sign of L in this first expression. Okay. Plus L z by 2 r square plus 3 L square z square by 8 r power 4 minus L square by 8 r square. Okay. And now this expression contains the difference between these two. Okay. This expression contains the difference between these two, which means that the temperature field is just equal to q by 4 pi k into the difference between these two. Okay. I think I made a mistake here. This should be this one should be plus, okay, and this one should be minus. Okay. Because when I take the minus half power, I will get a plus 1 by 2. Okay. And then there is a if I take the minus half power, I will get minus half into minus Lz by r plus L square by 4 r square. Okay. And I finally get Lz by r square as the result for this point dipole. Okay. Into z by r square. Okay. Which in a spherical coordinate system I can write it as QL by 4 pi k into cos theta. My apologies here, this should be r cubed because there is a 1 over r sitting outside here. Okay. So, I have to incorporate that 1 over r sitting outside here as well. Okay. So, this becomes r cubed. Okay. Cos theta by r square. So, therefore, in the limit as L becomes very small, but QL has to be finite. Okay. So, the requirement here is that L is much smaller than R, QL has to be finite. Okay. In that case, this is the solution for the temperature field. Okay. This is the solution for the temperature field. Okay. And the way that this will look is that you will have a point source plus Q, and you will have a sink minus Q separated by an infinitesimal distance. Okay. And you will have heat flux lines that originate at the source and then go to the sink. Okay. So, this is what is called a point dipole. The heat flux lines, they originate at the source and they terminate at the sink. Okay. Okay, and they are symmetric. Okay. So, they are symmetric, they originate at the source and they terminate at the sink. Okay. And I had shown you that in that expansion T is equal to sigma A n m r power n plus B n m by r power n plus 1 P n m of cos theta e power I e power I m phi. Summation n is equal to 0 to infinity, m is equal to minus n to n. Okay. If I take the term n is equal to 1, m is equal to 0, we get T is equal to A r plus B by r square. Okay. P10 of cos theta, okay. And P10 of cos theta was just cos theta itself, okay, was just cos theta itself, okay. So, this was just equal to cos theta itself. And this term 1 over r square times cos theta to within a multiplicative constant is identical to this one, okay. So, therefore, the source and sink separated by a small distance along the z axis corresponds to a point dipole, which is n is equal to 1, m is equal to 0 for the in the expansion of spherical harmonics. Okay. And also recall that when we did the problem for the heat conduction around a spherical particle, okay, when we did the problem of heat conduction around a spherical particle, when we wanted to evaluate the effective conductivity of a composite, we had a similar solution, right. We had T is equal to A particle r plus B particle by r square, okay, cos theta. This was the particle temperature. Matrix temperature was equal to A matrix r plus B matrix by r square into cos theta. Okay. Same as a point dipole. Okay. So, basically this term was 0 within the particle because the temperature had to be finite, okay, in order to satisfy the symmetry conditions at the origin. Otherwise, the temperature goes to infinity at the origin. Okay. So, this term had to be 0. Within the particle, it was just equal to A particle times r into cos theta. In the matrix, this first term was the temperature, imposed temperature. Okay. This first term was the imposed temperature far from the particle. Okay. This first term was the imposed temperature far from the particle. This second term here is the correction to the imposed temperature due to the presence of the particle. And this correction has the same form as the point dipole here. Okay. This correction has the same form as the point dipole here. Okay. So, in this spherical harmonics expansion for that particle, for the temperature field around a particle, what we basically did was that because there is a difference in thermal conductivity between the particle and the matrix, we know that there is going to be a disturbance to the temperature field. Okay. The heat flux lines in the undisturbed case look something like this. Okay. On top of that, we had imposed a dipole field. Okay. On top of this, we had added on a dipole field in such a way that the boundary conditions were satisfied. So, the matrix temperature was basically the temperature due to a constant temperature gradient, that is this first term here, plus a dipole at the center of the particle in order to ensure that the boundary condition at the particle surface are satisfied. Okay. So, that is a physical interpretation of a dipole. Okay. A source and a sink close to each other, distance goes to 0, Q times L goes to infinity in such a way that, okay, the net source is 0. Okay. You have plus Q and minus Q. If you go sufficiently far away, the net source is 0. If there were a net source, then the temperature would decrease proportional to 1 over r. When there is no net source, then the temperature field does not have a contribution proportional to 1 over r. The next higher contribution is 1 over r square. That was for a source and a sink separated along the z axis. Okay. What happens if you have a source and a sink separated along the x axis? Okay. Okay. So, along the z axis, we got T is equal to Q L by 4 pi k into z by r cubed, okay, or Q L by 4 pi k cos theta by r square. Okay. If you had a separation along the x axis, then you can just write the temperature quite easily by analogy. T is equal to Q L by 4 pi k into x by r cubed is equal to Q L by 4 pi k into sin theta cos phi by r square. Okay. And the next one, Q L by 4 pi k into y by r cubed is equal to Q L by 4 pi k into sin theta sin phi by r square. And if you had the source and sink in some other direction, okay, let us say that plus q at, okay, okay, if I had the source and sink in some other direction, let us say that the separation between the source and sink, okay, separation is Lx Ex plus Ly Ey plus Lz Ez. Okay. If the separation is in some other direction, you can just orient your axis to that direction and then do the calculation again. Okay. And basically what you will get is q is equal, and let us say this is equal to L vector, okay, q into L vector dotted with x vector. Okay. Is equal to q into Lx x plus Ly y plus Lz z by 4 pi k r cube. Okay. So, that is what you would get if the source and sink of equal magnitude was separated by some other vector L, provided the mod of L is much smaller than the mod of x. Okay. So, the dipole moment is what is a vector. Okay. It consists of these two terms. Okay. Is a vector which consists of q times L vector. Okay. This is the dipole moment. Okay, q times L vector is the dipole moment. Okay. So, the dipole moment dotted with x vector divided by 4 pi k r cubed is the temperature due to a combination of sources and sinks. Okay. Now, these things, the temperature due to these can also be written in terms of the spherical harmonic expansions. Okay. So, this will be equal to q L by 4 pi k, okay, into root of 4 pi by 3 into y 1 0 of theta and phi by r cubed. Okay. This can also be written as q L by 4 pi k root of 8 pi by 3 into y 1 1 of theta phi plus y 1 minus 1 of theta phi by r cubed by 2 r cubed, and this is equal to q L by 4 pi k root of 8 pi by 3 minus by 2 I r cubed, okay, where the y's were all I had listed them out here. Okay. Okay, if you recall, I had listed out those spherical harmonic expansions over here. So, just substituting in terms of x plus I y and x minus I y, I can write it in terms of these. Okay. So, the final point is that the point dipole are linear combinations of y 1 minus 1, y 1 0 and y 1 1, that is n is equal to 1, m is equal to minus 1 and plus 1. Linear combinations give you the dipoles in the x and the y directions. M is equal to 0 gives you the dipole in the z direction. Okay. So, that is for point dipoles. Okay. That is for n is equal to 1, m is equal to minus 1, 0 and plus 1. There are 5 of those. Okay. Okay, the next higher term is what are called quadrupoles. Okay. And I will just give you a brief discussion of that. I will not go into details. Okay. So, point source. is a source of energy. Q per unit time. Okay. Dipole point two. Okay, so one source plus Q and one sink minus Q. Okay. Separated by distance L. Okay. L is much smaller than the observation location. Q times L is finite. There are three solutions of these. For n is equal to 1, m is equal to -1, 0, plus 1. Okay. And these, the temperature field far away decreases as 1 over r. Okay. The next higher is what is called a point quadrupole. Two sources plus Q, and okay, so in this case T is proportional to 1 over r for r going to infinity. T is proportional to 1 over r square for r going to infinity. Okay. Okay. And two sinks minus Q, okay, separated by distance L. Okay. L is much smaller than x, and you will find that QL square is finite. Okay. And the temperature okay, so temperature proportional to 1 over r cubed. Okay. Okay. So in the expansion, this is okay, n is equal to 0, m is equal to 0. This is n is equal to 1, m is equal to -1, 0, 1. N is equal to 2, m is equal to -2, -1, 0, 1, 2. 5 of these. Okay. I will just discuss one of those, and that is the what is called the axisymmetric one. Okay. That is for m is equal to 0. Okay. I will discuss only the solution for one of those, which is the axisymmetric one, that is for m is equal to 0. Okay. The others you can sort of get by similar procedures. Okay. So, for the particular case where n is equal to 2, m is equal to 0. Okay. You have two sources at the origin, 2q, and one sink, okay, at plus L by 2, the other sink at minus L by 2. Okay. So, the distance between these is L. Okay. And then I have an observation point x over here, and I have to find out the temperature field due to the source, okay, over here, as well as these two sinks. Superposition once again. Okay. T is equal to I am sorry, I have reversed it. I should write it the other way. So, there are two sources at plus L and minus L. So, this is plus Q and I have minus 2Q here. Okay. So, the temperature field can be written as Q by 4 pi k into 1 by x square plus y square plus z minus L by 2 the whole square whole power half square whole power half minus 2 by x square plus y square plus z square whole power half. Okay. And recall that for each of these we had used an expansion, okay, and the expansion was that x square plus y square plus z minus L by 2 the whole square whole power half, okay, per is equal to 1 by r into 1 plus L z by r square. Okay. Plus 3 L square z square by r power 4 minus L square by r square 3 by 8. Okay. And similarly x square plus y square plus z plus L by 2 whole square whole to the minus half is equal to 1 by r into 1 minus L z by r square plus 3 L square z square by 8 r power 4 minus L square by 8 r square. Okay. Substituting that into this expression, I can find that the temperature field is given by T is equal to Q L square, okay, by 4 pi k into 3 z square minus r square by 4 r power 5. Okay. Alternatively, this can be written as Q L square by 4 pi k, okay, or L. Okay. And if you substitute z is equal to r cos theta, this also becomes equal to Q L square by 4 pi k into 3 cos square theta minus 1 by 4 r cubed. Okay. So, note that this is proportional to Q L square. So, in the limit as L goes to 0, Q L square has to be finite. Okay. This for a point quadrupole aligned along the z axis. How is this related to our expansion of the temperature field using separation of variables, the spherical harmonics expansion? I will continue this in the next lecture, okay? And I will also explain in the next lecture the other quadrupole moments. I will not go through the details of the derivation of those other quadrupole moments. I will just try to explain what those moments are and how they come about, okay? And with that, we will continue our discussion of the spherical harmonic expansions in the next lecture. I will see you then.